This is Lab 2, Motion of a Falling Object by Anthony Pisani. Our goals were to gather positional data on a thrown object using tracker software. We'll use this data to create two computer simulations of the experiment. We'll compare two models, one with drag and one without drag, to the tracker data to see which one was more accurate. Our possible sources for error include tracker miscalculations, limited frames per second on the video, and an inaccurate drag coefficient given to us by the TA. For the results preview, the computational model that accounted for drag and gravity was more accurate than the model that did not account for drag. Our key concepts were Newton's second law, force equals mass times acceleration, our velocity update formula, v final equals v initial plus f net over m times change in time, and our position update formula with drag. Our final position equals our position initial plus our initial velocity times time plus f net minus f drag over 2m times delta t squared. Our g coefficient is negative 9.8, and an important concept is that the force of drag always acts opposite to the velocity vector. The horizontal velocity does not change. For initial conditions and an overview, the system equals a 500 milligram weight plus the air. The surroundings were everything else. Our tracker recorded position every frame, which was about 0.033 seconds, plotted the x and y coordinates as a function of t. The tracker started after the object was let go, meaning the consistent net force equals 0. Our initial velocity vector was determined using our velocity formula, position final minus position initial over change in time equals velocity. Here were some of our graphs. This were the initial conditions for the code. The mass equals 500 grams. The position vector was given to us through tracker, and the velocity vector we derived through equations. Our b coefficient, which determines drag, was 0, as this model did not compute drag. We set our initial time equal to the same time given to us when the recording on tracker started, and we used our f net equals negative g times the mass of the ball. Then we used our velocity update and position update formulas to determine our graphs. These are the same equations given to you on the second slide. Here are our results for no drag. Our position horizontal versus time graph was a straight line because we had constant velocity in the horizontal direction, and our y position versus time graph closely resembled the position of the ball. This is because the marker was in the air for a very short amount of time, meaning drag had very little effect on it. These are our code initial conditions with drag. All initial conditions are the same except for b. B we set equal to 0.001, which was given. This value was given to us by the TA. We have to update our f net to account for drag. We kept our force of gravity, but we added a force of drag, which is negative b times v. So we coded the line negative ball velocity times b, which we just set in the slide before. Then we plugged this back into our velocity and position formulas. Here are our results with drag. It still closely resembles the path of the ball. And in the next slide, we will compare the two. Here are all three graphs combined on one plane. The red line is the tracker data, the purple line is the simulation with drag, and the blue line is the simulation without drag. As you can see, the purple line was closest to the tracker data, meaning it was a more accurate representation of the experiment. What does it mean? Did we reach terminal velocity? Our models do not run long enough to predict terminal velocity. Terminal velocity occurs when the force of drag equals the force of gravity, which creates no change in velocity. However, our velocity graph shows no sign of leveling out. We could generate a terminal velocity experiment by recording the position of our object for a much longer period of time, which means the force of drag has longer to act on the object. What if our object was thrown straight up? This means it would take longer to reach the ground. Our current velocity vector has some component in the x and some in the y. If we threw it straight up, it would have all gone in the y. This would increase the time it takes for the y component to reach 0. Conclusion: the drag model was more accurate in predicting the ball's motion than the model without drag, and we could not determine terminal velocity through the experiment due to a lack of time. Thank you.